All right, welcome physicists. As I've mentioned in other areas, we need to do 4.1 virtually. There's another prac that you need to complete. In order to do the other prac, you do need to have a little bit of information about series and parallel circuits. So I'm going to do it via this video. I hope you're all watching. And yeah, if you do have any questions, make sure you let me know at some point. So our learning intentions, we're going to be modelling resistance in two different types of circuits, series and parallel, and the formulas are just there. We're going to be looking at the effective resistance of circuits, and that is probably one of the more important things we'll be doing in this lesson. We're going to be comparing power transfers in series and parallel circuits and explain why the circuits in Ohms are mostly parallel. And so we'll be looking at the properties of series and parallel. Okay, so what are series and parallel circuits? Well, basically, they're two different types of circuits. Our components can be wired in series or parallel. We've already seen this a little bit because when we measure current with an ammeter, that has to be in series and voltage has to be in parallel. So a series circuit has all its components wired in the same loop. So what that means is, I'll just draw quickly, we have a circuit like that with a couple of resistors in it. So that's a series circuit. Our current goes through each resistor. It has no option. There's no branching paths. That's a series circuit. So those are two resistors wired in series. If we wire them in parallel, what that means is we have resistors like this. And so our current can either go through the first resistor or the second one. So each coulomb of charge will have a choice, and we'll come back to what that choice actually means. But each coulomb can either go through the first or the second, but each resistor will get some charge going through it. So a parallel circuit has junctions, whereas a series circuit, there's only one possible way that the current can flow through it. Okay. So here is our series circuit. The current flows through in one continuous pathway. So it'll go through, remember this symbol here is light globes. So the current here will go through each light globe. There's no option. All of the current will go through both light globes. Okay, so it goes through our first light globe, keeps going through that second ammeter and through the second light globe as well. So all current goes through both light globes. One of the main properties of a series circuit is that the current is the same in all parts of a series circuit. Okay, so it doesn't take too much imagination to see this, but whatever the current is going, let's do this again, whatever the current is going through this ammeter, the same amount of current will come out of the ammeter, meaning that will go through that light globe, the same amount will come out. It's just a continuous stream of current. So if we measure the current at any point in the circuit, we'll get the same value. Like that. Okay, the voltage in a series circuit, this is a little bit different. So the current in a series circuit is the same everywhere. The voltage isn't. So the way the voltage works is the voltage from the battery, so in this case 6 volts, whatever the voltage is in the battery, that is split between the components in the circuit. So we can see here we've got two light globes that are the same. So each one will have 3 volts of voltage going through it. Okay, so remember, voltage is potential difference. So what happens is we have a coulomb of charge that moves away from the battery, and remember that voltage is joules per coulomb. So this little coulomb contains 6 joules of energy. As it moves around our circuit, it will get to the first light globe, and it will need to expend 3 joules of energy to get through that light globe, meaning it will have 3 joules remaining. And then as it goes through the second one, it will use up those 3 joules and then go back to the battery for more. Okay, so if we measure the potential difference at each light globe, we'll get it at 3 volts. Now, if our components are different, you may get a different amount of voltage going through each one. So if we had 2 non-identical light globes, it is possible that the first would use 4 volts and the second would use 2. Okay, but basically this is something called Kirchhoff's loop rule. up there. So the sum of the potential difference across the components equals the battery voltage. Okay, so whatever the battery voltage is, that's how much voltage is going to be used in each component. So, as it says down the bottom there, as we add more bulbs, so if we added a third bulb that's exactly the same to our circuit, pretend that's in series, each one would then use 2 volts. And so the bulbs would each appear dimmer. So the more bulbs we put in, the dimmer each one appears because it is getting less voltage, okay, because it needs to be split. So, just to summarize, in a series circuit, the current is the same at all points. The voltage, whatever the battery has, that is split amongst the components. Okay. So, potential difference in work. So remember, work is just the amount of energy changed. And this is going back to that Kirchhoff's loop rule. So we have 6 volts in our battery, and that's exactly what I said in the last slide, completely accidentally. So again, the voltage across each lamp can add up to, well, must add up to whatever voltage the battery is doing. So the reason for this is, if you imagine a Coulomb of charge coming out of there with 6 joules of energy, if it, well, first of all, it can't go to negative energy, so it can't use, say, 5 volts on the first one and then 2 on the second, because then it'd be negative 1 joules, and we can't do that. It also has to lose all of that energy as well, because if it came out with 6 joules and, say, used only 3 here and then 2 here, it would go back in, gain another 6. So then it would go up to 7 joules the next time around, and it would keep gaining energy over and over again. And this violates quite a lot of thermodynamics. We cannot store energy in that way, and so the work that each Coulomb of charge does has to be equal to the energy that it gains from the battery. Okay, equivalent resistance. So this is something that's quite important when we're talking about series and parallel circuits. So in equivalent resistance, what we can have is, if you look at the left here, this is quite a complicated circuit. There's 7 different resistors in it, but any combination of resistors can be replaced by a single resistor of of some value. So if we work out there is some value that this RT would be, that would add up to the equivalent resistance of all of the other ones on the left. Okay, and I'll show you how to calculate those in a minute, but basically any combination of resistors could be replaced by a single resistor of the equivalent resistance of all of the resistors put together. Okay, the way we work out equivalent resistance is different in a series circuit to a parallel circuit. Okay, but we'll get to that shortly, and that'll make a little more sense when you see an example too. So here's an example. In a series circuit, to work out the equivalent resistance, we just add together the resistances of the resistors or the components that are in series. Okay, so in this case, we have 3 resistors in series. We can tell they're in series because the current only has one path to go through. It can't go anywhere else. To work out the equivalent resistance of these 3, we just add them together. Okay, so 10 ohms plus 20 ohms plus 15 ohms would give us an equivalent resistance of 45 ohms. So what this means, we could basically remove these resistors out of the circuit, replace them with a single 45 ohm resistor, and the circuit, the rest of the circuit, would function in exactly the same way. Okay, nothing would change. That's what we mean by equivalent resistance. We can take a group of resistors and replace them with a single one of the right resistance, and the rest of the circuit wouldn't change. There are many reasons why circuits have different numbers of resistors, but when we talk about the theoretical stuff behind it, that's what we mean. Okay, so we could remove those 3 and just replace it with a single 45 ohm resistor, and it would be exactly the same. So there is our formula to calculate the total resistance. So we use RT to mean our equivalent resistance or our total resistance. To calculate RT for any number of resistors connected in series, the formula is just we add them all together, the resistance of each one added together. Okay, so here we've got an example. We probably don't need to do this. It should be fairly straightforward, but let's just draw them. So we have 3 resistors. So we've got a 100 ohm, we have a 690 ohm, and we have a 1.2 kilo ohm. So remember, kilo is times 1,000, so that gives us 1,200 ohms. So, pretend they look vaguely like squares. So, those resistors connected in series, calculate the equivalent series resistance. So our equivalent resistance is equal to the sum of all of our other resistors, R1 plus R2 plus R3. Okay, so 100 plus 690 plus 1200, and that gives us, what is that, 1990. So we could remove those three resistors and replace them with a single 1990 ohm resistor. Okay, now I would like you to have a go at the try yourself here. So I'm not going to wait to do it because that's pointless on a video, but if you wanted to have a go now, you could pause the video, have a go at that, and make sure you're getting the right answer. I'll write down the answer in a second, and then we'll just move on. So if you want to have a go at this yourself, and I suggest you do, please pause it now. Okay, so the correct answer here is we have a string of Christmas lights. Our total resistance, well, again, we just add them all together. Oops, that should be R1. R1 plus R2, etc. So here we have 20 light bulbs, and they are all 8 ohms. So I'm not going to draw them in, but it's basically just, if each one is 8 ohms and there's 20 of them, we just multiply. Okay, so it's just all of them added together. We're just adding that 8 ohms 20 times, and so we get 160 ohms. Okay, another example. So use an equivalent series resistance to calculate the current flowing in the series circuit below and the potential difference across each resistor. Okay, so the equivalent resistance is not difficult. Here is where we get a difficulty spike pretty quickly. Okay, so make sure you're okay with equivalent resistance first, because things get a little bit tougher here. All right, so anytime you have a circuit, what you want to do, anytime you have a problem like this where you need to work out the voltage across resistors or the current in the circuit or anything like that, the first thing you need to do is work out the equivalent resistance of the entire circuit, and then use Ohm's law to work out the current in the circuit. Okay, so let's look at in our total circuit, we know that the total voltage in that circuit is 9. Our resistance in the total circuit is equal to all of our resistors added together. Okay, so we'll call this one R1, R2, and R3. Okay, so if we add all those resistors together, we get the total resistance in the circuit, which is 600 ohms. So we have V, we have R. To work out the current in the circuit, remember Ohm's law, I is equal to V divided by R. Okay, so if I is equal to V divided by R, that gives us 9 over 600, or 0.015 amps. So that's the current flowing in the circuit, okay, 0.015 amps, or we could say that's 15 milliamps. We'll leave it in amps for now because we need to do some calculations. All right, so first of all, calculate the current flowing in the series circuit. We've done that. Okay, so our current is 0.015. So just, again, you need to work out the total resistance in the circuit. You know the total voltage in the circuit, and so we can use Ohm's law, V equals IR, or in this case, I equals V on R, to calculate the total current. Now, remember we said earlier that each resistor will experience a voltage drop. Now, those voltages will need to add up to our voltage from our battery. So that's a good way to check that we've done this correctly. If our voltages add up to 9 volts, we're probably okay. Now, the voltage across those, we can't just say it's 3 volts on each because the resistors are not identical. They have different resistances, and so we cannot say that they are going to have the same voltage. In fact, they definitely won't. They'll be different. So how can we work out how much voltage goes into each one? Well, again, we go back to Ohm's law. Remember that our current here is the same current in everywhere in the circuit. It's the current in the total circuit, but remember the property of a series circuit is you have the same current flowing in every spot. So R1 has 0.015 amps flowing through it. So does R2, so does R3. We also have the resistances of R1, R2, and R3, so we can use Ohm's law to calculate the voltages. So the voltage across R1 we're going to call V1, and that is equal to I R1. So 0.015 multiplied by 100, and so that gives us 1.5 volts. Okay, so the current is the same going through all of them, so once you know the current, you can multiply that by the resistance to get the voltage. Okay, let's look at V2. The voltage across resistor 2 is equal to 0.015 multiplied by 200 this time, so we get 3 volts. V3, 0.015 multiplied by 300 gives us 4.5 volts. Okay, so let's just check now that these answers are okay. 1.5 plus 3 gives us 4.5, plus 4.5 gives us 9, which is the same as our voltage up there. Okay, so with a problem like this, the first step, and we're going to see some more complex ones later, so make sure you're okay with this one. The first step is to work out the current flowing in the whole circuit, and you need to do that by using the equivalent resistance. Find the resistance in the whole circuit, use Ohm's law to find the current in the whole circuit, then using that current you can plug it into the resistances and find the voltage that way. So you need to use Ohm's law in a couple of different ways with a problem like this. Okay, again, I would like you to try this one. Make sure you pause the video if you want to make sure that, well, pause the video, have a go at it yourself, and then unpause and I'll show you the answer. Okay, so again, same thing. Our current in the entire circuit is going to be 100 plus 690 plus 330. So our current in the whole thing is 1,120. Oh, sorry, not current, resistance. What am I saying? That's why I hope you've done it yourself. Our equivalent resistance is 1,120. All of our resistors added together. We know our voltage is 12, and our current is therefore 12 divided by 1120, which is 0.011 amps. Okay, now in this case I had to round a little bit. So when we add up our voltages again later, it may be slightly off, but that's okay just because of our rounding. Okay, if we didn't round it, it should be fine. Okay, so now if we look at our voltage across each one, V equals IR, so V1 is equal to 0.011 multiplied by 100, which gives us 1.1 volts. V2, 0.011 multiplied by 690. We get 7.59 volts. And V3, 0.011 multiplied by 330. I get 3.63. Okay, so again, if we add these together, they may not be exact, but they should be pretty close. So 3.63 plus 7.59 plus 1.1. And so, yep, I'm off. Well, I'm off by more than I thought it would be, 12.3. So I've rounded this quite a bit. If you actually did this yourself, you would have got 1.0714 times 10 to the negative 2. I've probably rounded that a bit too much, which is why our voltages are adding up to 12.3. But if you use that unrounded number as your current, you should get pretty exact. Okay, so that's how we do a series circuit. A parallel circuit is different. Okay, so here we have a parallel circuit, and we can tell it's parallel because our current has an option, which way it goes. So it can either complete the loop up there. Remember, the current just needs a loop, or it can complete that loop. Now, when we have a current in a parallel circuit, the current, when it reaches a junction, will split. Some of it will go down one path, some of it will go down the other. Now, in this case, it's split evenly because our two light globes are identical. Okay, they have the same resistance, so our current down each branch will be identical. However, if those two light globes are different, then we won't get even amounts of current down each. Okay, we might get 1.5 amps down one branch and 0.5 down the other. The higher the resistance is, the less current will flow down that branch. Okay, so Kirchhoff's junction rule. So Kirchhoff, he's named a couple of rules after himself that are fairly self-explanatory, but basically he's saying the amount of current flowing into a junction must be the same as the total current flowing out. So if we have a 3 amp and a 2 amp going into a junction, we'll get 5 amps coming out of it. If we have 5 amps going in, and then whatever comes out of it must be equal to, that 5 amps added together. So that could be different for different resistors. We could have 1 amp up here and 4 amps down here. Okay, but whatever it is, all the current has to add up to what went into the junction, what came out of the junction has to equal the same thing. Okay, so we see that in a parallel circuit the current is different. The voltage across each branch is the same. So again, this makes sense. Imagine you are a coulomb of charge and you have picked up 6 joules from the battery, and let's say you went through this junction. You've only got one component to spend your energy on, so you're going to spend all of your 6 joules there, and you'll come away with nothing. Or you could go the other way. You could go down this path, go through the light globe, spend your entire 6 joules there, and then go back. Okay, so each light globe will use the exact amount of energy per coulomb, so each light globe will have an identical voltage. Okay, so it's sort of reversed for a series circuit. So a series circuit, the current is the same at all points. The voltage adds up to whatever the battery voltage is. In a parallel circuit, the voltage is the same down each branch, and the current adds up to whatever it was before the branch. The interesting point here, though, is that because each light globe uses the same amount of voltage, it doubles the power output. And so our battery will run down faster, or will use more electrical energy. But because both of these light globes have the same voltage, the trade-off is they'll both be equally bright. So remember, in a series circuit, the more light globes we have, the dimmer they get. In a parallel circuit, we can put as many light globes in as we like. They'll all be the same brightness, but just the more we put in, the faster the battery will run down. Okay, equivalent resistance for a parallel circuit is a bit tougher to work out than in a series circuit. Not much, but a little bit. That is our equation. So 1 over the total resistance is equal to 1 over the first resistor plus 1 over the second resistor, and so on. So in our example here, our total resistance, or 1 over our total resistance. Now, by the way, the easiest way to muck these questions up is to forget that it's 1 over and just to say the equivalent resistance is equal to that. Okay, do not make that mistake. 1 over the equivalent resistance is equal to all of that. So if we add those together, we get, so 1 over our total resistance is 13 over 60, so therefore our total resistance will be 60 over 13, which is 4.62 ohms. Now, a good way to tell if you've done this correctly, your total resistance, if you look, should be less than every other resistance in the parallel circuit. The reason for this is we have, let's say, a 10 ohm resistor there, but it doesn't have an equivalent resistance of 10 ohms because our coulombs could just go through a different branch. So that 10 ohms is actually worth less than 10 ohms because we're not forcing the current through it. So basically, in a parallel circuit, each resistor, well, when we look at our equivalent resistance, the equivalent should add up to less than the original resistance. Okay, here's an example. A 100 ohm resistor is connected in parallel with a 300 ohm resistor. Calculate the equivalent parallel resistance. Okay, let's just draw it quickly just to make sure we're on the same page. So we're in parallel. we have a 100 ohm resistor and a 300 ohm resistor. Okay, so 1 over RT is going to be equal to 1 over R1 plus 1 over R2. So 1 over 100 plus 1 over 300. Okay, and if we calculate that, we'll get 0.0133. Actually, we don't need units for that because it's 1 over. So therefore, 1 over RT is equal to that. So therefore, RT is equal to 1 over that. And we will get 75 ohms. Oops, don't know what that line there is. Okay, so again, our 75 ohms equivalent resistance is less than the resistance in either resistor that we've got in parallel there. Okay, so again, the formula is a little more complicated than the series one. We don't just add them together, we do the reciprocals of each one. So 1 over RT is equal to 1 over R1 plus 1 over R2. Okay, again, I would like you to pause this video and have a go at this one, and then unpause and check that you've got the right answer. Okay, so I won't bother drawing this one, but our total resistance, 1 over RT, will be equal to 1 over 20 plus 1 over 50, which will be, oh, hang on, calculator errors at the moment. Okay, 1 over 20 plus 1 over 50. So 0.07 is what I get for that. And so therefore our RT will be equal to 1 over that, which is 14.3. And again, just to check, yes, our 14.3 ohms is less than either of the resistors we have there. Okay, so we're probably okay. It's a good common sense test. Okay, so resistance and current in parallel circuits. So what we have here in a parallel circuit, well, first of all, in the series circuit, if we have a particular battery, then let's say we have in a series circuit, we've got 2 amps coming through our first ammeter. And let's say this is a voltage of V. Without changing the voltage, if we then put in a second light globe, our current will actually increase. Okay, without changing the voltage, by putting in a second light globe, our current will increase. Now that sounds a little bit counterintuitive. You'd think surely it'd decrease if it has to go through more components. But no, remember, the equivalent resistance, the more objects we have in parallel, the lower the resistance overall is. And so if we consider Ohm's law, if we decrease that resistance for a particular voltage, we're going to increase the current. Okay, so the more objects we have in parallel, the lower the resistance is, so the higher the current will be. Okay, so different size resistors, this is what I mentioned before. If we have globes with different values of resistance, we'll get different amounts of current going through them. Now you can work this out via proportionalities, but it's easier to do it just by knowing the voltage and working out Ohm's law. So it hasn't given us a voltage here, but that's okay. So basically what I mean by proportionalities is if you've got a 1 ohm resistor here and a 2 ohm resistor here, we should have twice as much current flowing through there as we do through there. Okay, and this one should be halfway between them both. And if we have a look, A3, yep, 1.5 amps, we've got twice as much going through, and then between them. Oh, it's not halfway, but it's between them. Okay, so again, I wouldn't work it out via proportionalities, I would work it out with the voltage. And you'll never have to work this out without being given the voltage. Okay, another example. Now this is, again, one of those slight difficulty spikes where we did the series circuit. Here we're doing the same thing. So the overall steps we do are the same. We need to work out the equivalent resistance of the entire circuit to work out the current flowing through the entire circuit. And from there, once we know the current, we can work out everything else we need. Okay, so first thing, our voltage, this is going through our entire circuit. Our voltage is 12. Our resistance, remember 1 over RT is equal to 1 over 200 plus 1 over 100. So that gives us 0.015 ohms. And then to get our RT, we do 1 over that, which gives us 66.7. Okay, we'll just check. Yes, that resistance is less than either of the other resistors, so we should be okay. So that's our voltage in the overall circuit. We have our resistance in the overall circuit, so we can work out the current in the overall circuit. Remember, I is equal to V on R. So V, 66.7 divided by, oh, sorry, that's not V, that's R. So V is 12 divided by 66.7 gives us a current of 0.06. Oh no, sorry, I'm looking at the wrong line. Gives us a current of 0.18 amps, or 180 milliamps. Okay, that's the answer. So that gives us 180 milliamps, or 0.18. Again, it's better to leave it in amps for now because we'll be doing some calculations using that number. So we've got our current flowing in the circuit, okay, in the overall circuit. And then we need our current going through each resistor. Now, remember that in a parallel circuit, we cannot assume that an equal amount of current goes through each one. Okay, and we'll check our answer later, but we can use proportionality. So when we check this out, we should see twice as much, we'll call this R1 and R2. We should see twice as much current go through R2 because it's got half the resistance. But let's actually calculate it. Remember, in a parallel circuit, the voltage drop across each branch is exactly the same. So therefore, the voltage going through R1 is going to be 12 volts. The voltage going through R2 is also going to be 12 volts. All right, remember we spoke about that when we looked at the voltage in a parallel circuit. So the voltage going across each one is going to be 12. So now we can use Ohm's law again to work out the current going through each one. So the current going through R1 is going to be V1 over R1, which is going to be 12 over 200. So that is going to give us 0.06 amps. I2, so the current going through the second resistor is V2 on R2. V2 is still 12, R2 is 100, so that is 0.12. Okay, so a couple of tests we can do here. First of all, our proportionalities. We guessed originally that twice as much would go through R2 as R1, and yep, that's exactly what we're seeing. Also, remember Kirchhoff's junction rule. The amount of current going into a junction has to be the same as that coming out. We figured out the total current in our circuit, so our current up there is 0.18 amps, and so that goes into this junction here, and so coming out of it, we should have 0.18 amps. So both of our currents should add up to 0.18, which they do. Okay, again for this one, I would like you to pause the video, have a go at it yourself, and then turn it back on and check that you are correct. All right, so for this one, our equivalent, or our voltage in our whole circuit is 10. Our equivalent resistance, I'm going to skip a couple of steps here. Hopefully you're okay with this. Oops. So I get the equivalent resistance to be 18.75. Okay, and again, we're less than both of them, so we should be okay. So we've got our voltage, we've got our equivalent resistance across the entire circuit. So I equals V on R, 10 divided by 18.75, and I get 0.53. Okay, again, I'm rounding this, so the answers we get further on may not be exact, but they should be pretty close. Okay, but it's actually 0.53 recurring, but we're just going to call it 0.53 for now. Okay, so we know our current in our whole circuit. We know the voltage is 10 volts, and remember that the voltage going through each resistor has to be the same. So the current going through resistor 1 is going to be V1 on R1, so 10 over 30 gives us 0.33, and then I2 will be 10 over 50, which will give us 0.2. Oh, look at that, it's worked out exactly. So we can see there, again, from Kirchhoff's Kirchhoff's junction rule, the current going through each branch should add up to the total current in the circuit, which again, they do. Okay, so hopefully you're okay with that. Okay, these last examples combine components or combine series and parallel circuits, and these can be quite tricky and quite time consuming. The way you need to do a problem like this is through, well, some creative use of equivalent resistance, and then our steps are the same. But overall, the first thing we have to do, again, is to work out our equivalent resistance. Now, these two bits here are in parallel. So what we can do is work out the equivalent resistance of those two resistors. So remember, equivalent resistance just means we can replace them with one resistor. Okay, one particular resistor to work out, to replace the 30 and the 40 ohm. So let's work that out now. So we have 1 over the equivalent resistance. I'm just looking at this particular spot. It's equal to 1 over 30 plus 1 over 40. So the equivalent resistance of that circle is, well, overall that is 0.058. And so 1 over that. So our total resistance is 17.14. Okay, so what I could do for this circuit is replace the 30 and the 40 ohm resistor in parallel with just a single 17.14 ohm resistor, and that would work. So let's say we do that. Let's say we replace the 30 and the 40 with a 17.14 ohm resistor, and all of a sudden, look at this now, we have a series circuit. Okay, so anytime you have a combination, look at the resistors that are in parallel, work out the equivalent resistance of just the ones in parallel so that we can replace them and make it into a series circuit. So now, over here, we'll do our total voltage in our circuit is 12. Our total resistance in our circuit, again, we've gone back to a series circuit. Because we've replaced everything in the circle with one resistor, now we can just add them together. So 20 plus 17.14 plus 10. So that is 47.14 is our total resistance in our circuit. Our total current in the circuit is therefore 12 divided by 47.14. And so our total current in the circuit will be 0.254 amps. Oops, that can't really see that 4. 0.254, there we go. All right, so we know the total voltage in the circuit, we know the total current, and we know the total resistance. So now we want the potential difference and current through each resistor in the circuit below. So let's do these one by one. So R1, we know R1 has 10 ohms. Now R1 is just part of a series circuit, and we remember that the current anywhere in a series circuit is the same. So 0.254 amps. Now the voltage across R1, we need to calculate this through Ohm's law. Okay, remember our series circuit, all of our voltages will add up to that 12. We don't know they're all the same, we know they'll add up to that 12. So our voltage is going to be equal to 0.254 times 10. Okay, current times resistance. Okay, V equals IR. So that gives us a voltage drop of 2.54 volts. Okay, so there is resistor 1. Oh, I'm going to run out of room here. I'm going to try and write a bit smaller. There's resistor 1. For resistor, well, we'll leave 2 and 3 for last because they might be the tricky ones. Let's look at resistor 4. Resistor 4 is 20 ohms. The current going through resistor 4, we know, is also 0.254 because again it's in series. The current across everything in series is the same. So our voltage will be 0.254 multiplied by 20. So that will be, where are we? 5.08. Okay, so we've got R4 worked out. We've got R1 worked out. So now, a little bit trickier. So, looking at our, let's look at this junction. Okay, let's look at that junction. And we know that the resistors in that junction are going to have the same voltage drop. But what is that voltage drop going to be? Okay, again, pretend that we have replaced it with a 17.14 ohm resistor. And now, hopefully we can see that the voltage drop is going to be equal to IR. Okay, so if we had replaced the 30 and the 40 ohm resistors with just a single 17.14 ohm resistor, then we can just work this out the same as we would with a normal series circuit. So V equals IR, 0.254 multiplied by 17.14. And this is the voltage drop just in the circle that I've drawn. Okay, so V equals IR, 254 times 17.14 is going to equal 4.35 volts. All right, now again, remember that the voltage at all points of a series circuit should add up to the voltage in the battery. So now we have the voltage across all parts of our series circuit. They won't add up exactly, but they should be pretty close because again, rounding. But if we add those together, 8 plus 4.35, we get 11.97. Okay, so instead of 12 volts, 11.97, that's pretty close. So we can test that way. We know we're going okay. All right, so in all our previous calculations, we pretended that we replaced our 30 and 40 ohm resistors with a single resistor of 17.14. So that's the first step, is pretend that everything in parallel, pretend that you can replace it with a single resistor. Now, we need to work out actually what's going on in R2 and R3. Well, first of all, we know, well, let's look at R2. We know R2 is 30 ohms. We also know that anything in parallel or down each branch, we lose the same voltage, or we have the same voltage measurement. So R3 and R4 are going to measure the same voltage. R2 and R3 are going to measure the same voltage. So if we have 4.35 volts going into it, then that is what is going to be lost across each branch. So our voltage is going to be 4.35 volts. From here, Ohm's law will tell us how much current goes down each branch. So 4.35 divided by 30 will give us 0.145. 0.145 amps. Okay, so that's the current going through our resistor 2. For R3, we know it is 40 ohms. And again, it's in parallel with R2, so they have to have the same voltage going through them, 4.35. And again, if we do V divided by R, just rearranging Ohm's law again, that will give us 0.109. Okay, now again, from Kirchhoff's junction rule, the amount of current going in to a junction should be the same as the current coming out. So we know that going into our junction, we had 0.254 amps, because that's what the current was along all these points. So our two currents here should add up to 0.254 within rounding. And if we add those together, we'll see that's exactly what they add up to. Okay, so this is a more complicated one. The first step with doing a problem like this is replacing anything in parallel with a single equivalent resistor, working out your current in your circuit that way, pretending it's a series circuit to that point, work out your series resistors first, the voltage and the current across those, then pretend your your equivalent resistor again is in series, so you can work out the voltage drop across that. That voltage drop will give you the voltage drop across each branch of your parallel circuit, and from there you can use V equals IR to work out the current. Okay, this one I'm not going to work out straight away. I'm going to give you some time to work this one out, or I'll put up the answer somewhere shortly, but I really want you to have a go at this before you check the answer. So I'm not going to record the answer here, but I really want you to have a go at it. It's quite challenging, but remember, you need to replace those with equivalent resistors, and from there, see how you go. Okay, so one of our things that we had to do in this section was to compare the power drawn in a parallel circuit compared to a series circuit. So let's have a look. Consider a 100 ohm and a 300 ohm resistor wired in parallel with a 12 volt cell. Okay, let's do it. So we have a 12 volt cell, 12 volts, we have 100 ohms, and we have 300 ohms. Calculate the power drawn by these resistors. Compare this to the power drawn by the same two resistors when wired in series. Okay, so if they were wired in series, they would look like this. 100 and 300. Okay, so we need to compare the power drawn by both of these circuits. So remember, power is equal to IV. All right, so if we look at these, the power dissipated in the circuit, well, first of all, we're looking at the whole circuit here. So the power dissipated in the circuit, we know what the voltage is, we just need to look at the two currents, and we need to calculate those with equivalent resistance. So let's look at our parallel circuit first. 1 over RT is equal to 1 over 100 plus 1 over 300. So that will give us, remember, 1 over all of that will give us a 75 ohm resistance. Whereas, if we look at our our series circuit, our equivalent resistance is all of our resistors added together. So 100 plus 300 is 400 ohms. All right, so straight away we can see that the parallel circuit has much lower resistance. And so if we consider V equals IR again, if we have a much lower resistance, we should have a much higher current. Okay, and if the voltage is the same, but the current is higher, the power should be higher as well. So let's just double check all of this. So our current in our parallel circuit is going to be equal to 12 over 75, which is 0.16 amps. And so the power dissipated in that circuit, power is equal to current times voltage, 0.16 times 12 will give us a power of 1.92 watts. Now if we compare that to a series circuit with the same resistors, here our current is equal to, again, V on R, 12 on 400, so our current is going to be equal to 0.03, and then our power is equal to current times voltage, 0.03 multiplied by 12, 0.36 watts. And so we can see the power dissipated in a series circuit is much, much lower than the power dissipated in a parallel circuit. The trade-off, though, remember, is that in the parallel circuit, all lights will glow with the same brightness, whereas in a series circuit, the more lights we add, the dimmer they get. Okay, so that's why the series one uses less power. So yeah, it'll use less power, but the more globes we add, the dimmer each one gets. The other one, the parallel circuit, we can add as many globes as we like. They'll all burn as brightly as each other, but we'll use more power doing it. Okay, again, this one I'm going to leave for you to try. Have a go at this with everything you've learned so far. I'm not going to record an answer just yet, but I'll put the answers up somewhere. Okay, finally, we're going to be looking at the failures in these circuits. So remember that in a series circuit, our current only has one path. Now, what happens in a series circuit if one of our light globes here has burned out? And there's no real symbol for this. So I've just got rid of one of the lines in the light globe to demonstrate that it's burned out. So if this globe has burned out, all of a sudden, our current has no path. It can't flow past that point. And so nothing in this circuit is going to work. You'll get no current, red, at all of those ammeters. Okay, no current at all. And this globe will not work. So there is no current. If a component burns out in a series circuit, there is no current at all. Nothing will work. Now, this you may have seen on TV. Old Christmas lights used to be wired in series because they used less power. But the problem with that is if one light burnt out, the whole line, might be several hundred lights, none of them would work. And so we have this staple of American Christmas movies where you have the person going through the entire line of light globes trying to find the broken one to make everything else work. Thankfully, they're no longer run like this. Basically, every type of Christmas light now is run in parallel, which we'll have a look at on the next slide. But yeah, the idea in a series circuit, if you take one component out or one component stops working, everything will stop working. Conversely, in a parallel circuit, the components will all work. Well, everything that doesn't die will still work because the current still has a path to flow. So again, here is our burnt out globe. So current can no longer go through this loop. That's fine because it can still follow the red arrows. It still has another path that it can follow. So if we have two light globes in parallel and one of them burns out, the other one will still keep going because current can keep flowing like that. Okay, so this is why it's really good that Christmas lights are now wired this way, because if one of them burns out, every other light in the circuit will still work, and it's pretty easy to identify which one has burned out. Now, interestingly, this is how household wiring is done. So if you consider all the appliances plugged into your house, if they were all connected in series, turning one of them off would make everything else not work, because that would be where the current stops at the appliance that's turned off. So that would mean you'd have to have everything running all the time and hope nothing broke. Instead, we have things running in parallel, as you can see in this diagram here. So we have our main supply. So our current can go through any or all of these paths. So we can turn on the TV, and that means that current will flow like that. If we wanted to turn on the heater as well, then our current would flow like that, and we could still turn off the TV if we wanted to, and we'd still have this current going through our heater. So all household wiring is in parallel because it just means that we don't have to have everything on at the same time. Okay? If one thing is off or if one thing's broken, everything else is still going to work. Okay, here is a summary. So it's really useful to remember these summary points when you are doing these calculations, and especially for the prac that's coming up. So in a series circuit, the current is the same at all points of the circuit. The voltage from the battery is split across all components. So if you have 6 volts in your battery, all of your components must use a total of 6 volts. And a single failed component will stop every component working. In a parallel circuit, the current is split at junctions. So The current at each junction will add up to the current going into that junction. The voltage across each junction is the same though, so across each side of a junction. So if one light globe is using 6 volts on one side of a junction, then across the other side, the other light globe will also use 6 volts. It doesn't matter if they're the same resistance, they'll both use the same amount of voltage. And if any component fails in a parallel circuit, the others will continue to work. All right, that brings us to the end of 4.1. I know there's a lot of information in there. It's taken quite a long time to go through. Have a go at those last couple of try yourselves. Make sure you're okay with everything leading up to those, otherwise those will be really difficult. And then that will hopefully lead you in nicely to the prac that I'm going to send out as well. If you have any questions, I know it's difficult learning like this without being able to ask questions face to face. If you do have any questions about this stuff, please email me. Otherwise, good luck with it all, and I'll hopefully see you first day back of term 2.